Good morning, all. Today I'm going to be telling you the story of a problem that started when I was 11 years old, and I'm still working on it. It's called Motley Dissections, and at the end you'll find out why it's called that. So when I was in 6th grade, our teacher gave us some little squares or rectangles of paper and said, make a bookmark. We're having a contest. Who can draw the best one? I decided to cut mine up and make a puzzle. Here's what I made. I wanted to make the hardest puzzle I could with the fewest number of pieces. This was not bad for a start. It turns out a standard dissection. I really like the edge on the left because there are 3 pieces that meet along that green edge. And that means you cannot put this, assemble this puzzle by just taking 2 pieces with the same edge length and putting them together and saying, oh, they must go together. But the purple edge on the right, not so good. 2 edges do share a complete edge. So I wondered, is it possible to do a dissection where no 2 pieces completely share an edge? I called them non-sharing dissections, but I didn't like the name. Well, the answer is yes, you can do it. The most famous example is the squared square. A square cut into smaller squares, all of which are different sizes. Of course, no 2 completely share an edge there because then they have the same edge length. Unfortunately, and Martin Gardner wrote about it, I learned about it in his column, it's impossible to cube the cube. You can't cut a cube into a finite number of smaller cubes. So I wondered, what can you do with other polygons? So I did a lot of doodling. Triangles. Yes, you can cut there's a Motley dissection of a triangle into triangles. And you can cut any of those triangles, so you can do larger numbers as well. Can you cut a triangle into quadrilaterals? You can. This is the smallest dissection that has only convex quadrilaterals, but maybe one of you can do better. The reverse is not possible. It's impossible to cut a convex quadrilateral into triangles in a Motley manner. Quadrilaterals into quadrilaterals is the easiest case. You saw the squared square, but you can also rectangle a rectangle this way, very common dissection. Pentagons, a little harder. It is possible, but here's how it works. 1 in the center, 5 around it. Those are 5 concave pentagons, not overlapping triangles. And then 5 more around that. Takes 11. And beyond that, hexagon into hexagon is impossible. Larger numbers stay impossible for more or less the same reason you can't tile a sphere with hexagons or heptagons. And the proofs all involve Euler's relationship on polyhedra. Vertices minus edges plus faces equals 2. So speaking of polyhedra, you may have noticed, it really struck me that these 3 Motley dissections across the top look a great deal like the Schlegel diagrams, the flattened versions of 3 of the Platonic solids. I wondered what was going on there. Well, remember that Platonic solids have duals. Here's the cube, it's dual to octahedron, and what's going on is each face in the cube becomes a vertex in the octahedron. I've color-coded so you can see that, and faces map onto vertices. Everything's inverted. For instance, this corner of the cube has 3 edges coming out of it, and it corresponds to this triangle on the octahedron, which has 3 edges. There's a 3-ness there. So here's another view of the cube, 8, 12, and 6, vertices, edges, faces, and it corresponds to this figure, and it's completely isomorphic. The 6th face, by the way, on the cube is the outside, and the same is true on what I'm calling here the pseudo-cube. But this time, the faces map. There's 6 four-sided regions in both figures, but now on the right, there are 8 edges and 12 vertices. So this vertex on the left has 3 edges, and on the right, you have an edge with 3 vertices. Here's the octahedron, the pseudo-octahedron. Here you have to start going curvilinear. The outside of the pseudo-octahedron is a concave curvilinear triangle. the tetrahedron and its pseudoduals. It has a third pseudodual, which is really strange. It's made up of 6 digons. 5 digons, curvilinear digons make up of 6, and they're all in a motley arrangement. Well, why stop there? If 3D polyhedra make 2D Motley dissections, what about 4D polyhedra? As many of you probably know, there are 6 regular polyhedra in 4 space. The simplest one is the 5-cell. It's the tetrahedron with an extra vertex in the center. Of course, that's not really in the center. It's a distance up in the w-axis. But in this projection, it appears to be in the center. It has 5 vertices, 10 edges, 10 faces, and 5 cells, 3-dimensional cells, which are themselves tetrahedra. And you can see it. There's 4 tetrahedra meet at the center, and then the exterior is the 5th one. Well, in the pseudodual relationship, the cell stays cell, so it's still going to be 5 tetrahedra, but vertices, edges, and faces all invert, which is a conventional dual. And it looks like this. They're curvilinear. The exterior is a concave tetrahedron. I'll show you how it's constructed. Start with the tetrahedron, extend the bottom face, extend the back face, extend the left face, and extend the right face, makes these. Those are not all congruent. 2 of them are the same. And then surround the whole thing with a sphere and puncture one of the 4 regions, and you get this figure. And it comes apart like this. Haven't 3D modeled this yet. I plan to do that shortly after the conference. I won't go into detail on these.
Scott?
Excuse me?
Need to wrap it up.
Okay.
If you can.
So here are some of the other pseudoduals. The octahedron, the 24-cell has octahedral faces. Those invert to become boxes, and that's the figure that, that's this figure. It has 23 boxes that make up a 24th. Bill Cutler also discovered this. He called it the boxed box. I'm calling it also the Motley cube. And Donald Knuth called them Motley dissections. He called me up a year ago, dug up my Gardner correspondence, and you'll find this as a transparent cut and assemble model in your gift. Thank you.